Okay, it's we're live now. So Rahul, please feel free to introduce.
Okay. Welcome everyone. So today we are going to have the first student's presentation. So the first student is Talu. Talu is a master student in ETH, and he's going to discuss about the recent work called Bandit, lightweight and reusable reinforcement learning for microarchitecture decision making. So yeah, you're going to see something that we have on the same direction of what we have discussed in past few lectures, that use of machine learning techniques, lightweight machine learning techniques, reinforcement learning to be specific, on various aspects of the computer architecture. And Talu is going to discuss more about this work. Hey, Talu, the stage is yours.
Thank you very much, Rahul. First of all, I want to say I'm delighted, but I'm not a master's student yet. Maybe after the seminar, I will be. I'm currently a bachelor student for everyone. It's, first of all, delightful to see everyone here. I think way more people than usually. And thank you, Rahul, for the nice introduction. Let's get started. As Rahul has said, machine learning, especially artificial intelligence, has had a major role in computer architecture these last years. This is why I want to present today Bandit, lightweight and reusable reinforcement learning for microarchitecture decision making. Before going into the paper, let's begin with a quick executive summary. As I said, reinforcement learning has been effectively integrated into many various challenges in microarchitecture. Current solutions have two key shortcomings. One, they have a high complexity and storage overhead. This stems from bookkeeping, many states, actions, and transitions. And two, RL agents are tailored for specific applications and lack reusability. The goal is to design an RL agent with the following characteristics. One, lightweight, which emphasizes efficient microarchitectural design and minimal resource consumption. And two, reusable, meaning effortlessly applicable to multiple microarchitecture problem domains. The contribution of this paper is Bandit, a lightweight and across multiple microarchitectural problem domain reusable RL agent that provides a lightweight design due to only considering a small fraction of the action space in a given time window. The specification is called temporal homogeneity, which we're going to discuss later. And two, provides ease of design and implementation, easily applicable to different problem areas. The evaluation of this RL agent that can work on multiple problems is done on two problem domains. One, data prefetching, and two, instruction fetching in simultaneous multi-threaded processor. MAB outperforms non-reinforced learning prefetchers by 2.3 to 2.6% and attains similar performance to RL prefetcher Pythia. Important, it also improves by a lower storage requirement of only 100 bytes, meaning I think Pythia's storage requirement is about 26 kilobytes per core, so that is way, way better. And for instruction fetching, MAB outperforms the choice policy by about 2.2%. So this is the structure of my talk. First, I'm going to talk about the two problem domains we're going to focus on and about current approaches and their shortcomings. Then a bit more about reinforcement learning for data prefetching and instruction fetching, Bandit, an overview of the structure, and then we'll go into evaluation, conclusion, and the critical analysis at the end. Just to refresh your memories, data prefetching is predicting addresses of long latency requests and fetches the data before the program actually demands it. And this means we have some access pattern from past memory and some context information on which we want to predict future access patterns. I mean, there are a lot of program features that could help us in these cases. We have the program counter, we have the page number, we have the page offset, and many, many more that you could imagine. Usual shortcomings in prefetchers these days are that they mainly use a single program feature, and two, that they lack inherent system awareness. This is the reason why I think 2 or 3 years ago, Pythia was developed by Safari, which is formulates this whole prefetching as a reinforcement learning problem. I'm going to come into that a second later, but Pythia has negligible power overhead, but requires about 26 kilobytes of metadata storage per core, which in limited systems is actually quite a lot. There are also, in this whole reinforcement learning agent, non-adaptive features that Pythia integrates, For example, this simply the degree selector that selects how many lines you want to prefetch. It's just to show you that not everything is controlled by reinforcement learning. Okay, perfect. This slide you've probably maybe even seen. This is how Pythia basically models this prefetching as reinforcement learning. We have an agent, which is a prefetcher, and this is inside of an environment, a processor, or the memory subsystem in our case. Obviously, we have some state, which is the feature of a memory address. As I said, basically, for example, the program content in our case. And obviously, as an agent, I can take an action, which means I can actually prefetch the lines I want to prefetch. And then we have, obviously, after an action, we get the reward on basically how good our prefetching actually was. Okay, so now we have talked a lot about prefetching. Let's context switch for a second to the second problem domain, which is instruction fetching in multiple processes, in SMT processes. These have the facility that we can work with multiple threads concurrently, meaning we have to decide from which thread we actually want to pick the next instruction. Again, there are many ways to break the ties. There are the branch counts, instruction count, entries in the load still queue, etc., etc., etc. But what we are going to focus on is actually a very smart way, and it's, I think, an adaptive mechanism presented in 2008 by Choi and Young, and it talks about the fetch priority and gating of threads. So on the bottom, you can see the whole system here. It looks a bit complicated, but I'm going to break it down for a second. So in main part, we have two options. This whole system consists of two blocks. One, the fetch gating that you can see here in red, and two, the fetch priority that is here in blue. Imagine all of the threads you have are a kind of a pool. The first exercise is to narrow this pool down. This is what the red block is for. We want to gate threads and coming to the next step, so we have fewer threads to decide which one we should fetch the instruction from. Then the question becomes obviously, how do we decide which threads to gate? And this is by the usage of certain structures. For example, in this example, here, we have the instruction queue, the integer register file, and the reorder buffer. If a thread exceeds the threshold of usage of one of these structures, it gets gated and it cannot progress into the next part. The remaining threads, we simply break the ties by looking at the instruction count and then deciding which thread we want to progress with. Then there's a small little green part on the right. This is for deciding what the threshold actually of these structures should be. I talked about structures and about using these structures, and this hill climbing algorithm that you may know from genetic algorithms that decides how we should change the threshold from iteration to iteration. This whole process actually has obviously some drawbacks, which is one, in total, the low adaptability. We only use instruction count here to break the ties, and two, the structures which we monitor during the gating process are fixed. Just to keep it in your head for the future. Okay, now we discussed the problem domains a lot. Now let's get into actual reinforcement learning. Now, in reinforcement learning, there are different problem formulations. Meaning, here on the left side, we have one that you've already seen, and it's called Markov decision process reinforcement learning. This is based on Markov chains. You work with algorithms of probabilities. What it basically is that we have multiple states that actions lead to non-determined transitions between the states, and then also each action, depending on the state, leads to a different reward. These whole structures, these formulations, lead to extremely high complexity, from bookkeeping all the action values, all the states, state resistance, etc., and is actually quite hard, quite bad to implement in hardware. Pythia is one example for a paper that actually uses these Markov decision process reinforcement learning formulations. Let's get to the next stage, which is contextual bandits. Contextual bandits are a bit more lightweight. They remove the straight transition probabilities, which means now to transform from S1 to S2, for example, can still happen, but it is not influenced by the agent's actions. It can happen, for example, randomly. And the third part, and that's the interesting part, are multi-armed bandits. Multi-armed bandits collapse the whole environment to a single state, which means the reward only depends on the action you take. The agent's choice is basically independent from the context and external factors. If you would now compare these formulations side by side, we would say, okay, from right to left, we obviously get way more expressive. We can understand more complex relationships, where from left to right, we get more lightweight and it's easier to implement than hardware. Since we are talking about hardware here, the best case for us would be multi-armed bandits. The question now becomes, are multi-armed bandits good enough to use these in microarchitectural problems? And the answer is a bit complicated, but yes, if the problem domain has specifications, I guess I could say. And consider a scenario where the same action of or prefetcher, for example, is repeatedly optimal for a large enough period inside an RL episode. One could say that currently the action is temporarily optimal regardless of the environment we are working in. This feature is called temporal homogeneity of the action space and allows us to reduce the environment state to a single state, since only a few actions suffice to model the action space in a given fixed time window. A simple example can be here. On the left side, we have a fully temporal homogeneous action space in episode 1 and episode 2. On the right side, we have a heterogeneous action space. It is important to say that not the whole episode of the RL agent needs to be temporal homogeneous. Only fractions in a specific time window. So the time window can be larger, it can be a bit smaller, but in general, it should be not pseudo-random or random, as you can see on the right side. Okay, now the question actually becomes, okay, we have said that we can use multi-armed bandits if we have temporal homogeneity. But do our two problem domains, data prefetching and instruction fetching, actually have these? The paper solves this problem quite easily. As I said, we have Pythia, which is our state-of-the-art baseline prefetcher. And what we do is we monitor all 64 actions of Pythia and simply check how often the most repeated action is actually returned. And then how often the second most repeated action is returned, etc., etc., etc. And we get the following nice graphic. On the x-axis, we have the different applications. On the y-axis, we have the percentage of actions. And black, you can see the most returned action. And on the black and white, you can see the second most returned action. And if we go exactly to the right and average all these applications out, what we see is quite interesting. It is that the most selected action accounts for 60% of all actions, and the second most selected action for 15% of all actions. This means 75% of all actions can be modeled by simply 2 actions. This sufficient temporal homogeneity allows us to use MAB for data prefetching by the kind of coordinator of various conventional lightweight prefetchers. Okay. Now, again, we need a context switch. Let's move again to instruction fetches. So, as I said, we have different policies. So we have first fetch gating and fetch priority. Just to remember for you, fetch gating is to gate a few threads that then goes to the fetch priority, and then it gets decided which thread gets executed. I've said that the choice of structures was static before. So now, actually, you can see, for example, for this policy here, everything, we monitor every structure, whereas for the first policy, we actually look at no structure essentially. So what we do is the following, quite easy. We create a few of these different policies with different priorities and different structures, and then monitor how good they actually perform on, again, a set of workloads. And what we see is quite interesting. It is, again, x-axis you have workloads, y-axis you have at 0%, the non-changed choice policy or performance. The line on the top is the best performing policy from all the policies we've created, and the line on the bottom is the worst performing policy of all the policies we created. And we can see that there's actually a high benefit of changing policies depending on the workload, which is up to 30%. But it's also important to say that choosing a wrong policy can stop a performance up to 40%. Which in our case, I mean, we have to be very, very good at what we do. Otherwise, we'll cause more problems than we actually solve. Okay, now we have talked a lot about this. Let's totally get into Microarmed, bless you, Microarmed Bandit. So, multi-armed Bandit algorithms are very easy to implement. We require only M arms, and we have 2 tables, R and I. The table N is for the number of times arm I has been selected. The table R is the average reward arm I has given us in the past. First, when initializing the algorithm, we had a round robin phase, which means each arm is selected once, and we consecutively fill first entries into R. And the second part, the main loop, simply repeats until the episode finishes. We choose the next arm, we update our selection, and then we update the reward that we get from the system. And then again, obviously, we continue until we're finished. So choosing the next arm, updating selection, updating the reward is not that simple. There are many ways you could do it. Here, I've only picked 3, but there are, I guess, many more. But what is important to know is that, I don't want to go in depth here, but we can afterwards in the FAQ if you want. What is important to know is that these have a different exploitation trade-off that you might have seen from natural programming or from from genetic algorithms also. In this paper, it's important that we've actually worked with a discounted upper confidence bound, which allows us to have a very nice converging solution in the end. There's also an exploration analysis done in the paper that shows that the right one is called upper confidence bound works best, but yeah, I've brought it into my backup slides if anyone wants to discuss it. Okay, so now, since we're talking about microarchitecture, how would we build these things? And it's also quite simple. We have 2 tables, 1 arithmetic unit, and some control logic. The 2 tables are the tables we discussed before. The arithmetic unit calculates the next arm, the update selection, and the update reward. And the control logic triggers a selection of the next arm, communicates the arm, and then also communicates the reward. Simple. I mean, on the left side, you can also see how it's implemented, but I will just skip this for a second since we're a bit low on time. Okay, so now let's get to the use cases on how we want to exactly use this for prefetching. I've said to you, instead of actually using the reinforcement learning tool to calculate or guess the offset and the degree, we will use MAB as a coordinator for 3 prefetchers. 1, the next line prefetcher, 2, the screen prefetcher, and 3, a PC-based prefetcher. The action basically that we have is in every move is this. We choose an arm ID, we have 11 arms here. An arm ID encodes if the next line prefetcher is on or off, it encodes the degree of the sprite prefetcher and the degree of the screen prefetcher. Note that please, if the degree in one of those cases is 0, this means that the prefetcher will be off for this arm. Yeah, and the reward that we get will be the instructions per cycles that have been committed since the last step this Bandit loop has been done. I guess this is quite straightforward. Let's move to the next slide. SMT instruction fetch use case here. I guess I said again, we control the priority and gating policy. We have these different, this would be basically one arm, this would be another arm. And then we control the priority, fetch gate again. Yeah, and the reward as before is the instructions per cycle. Additionally, it's important to mention that I said hill climbing algorithm is used for thresholds, and this doesn't change. Also here, we still use a hill climbing algorithm to set the thresholds each step or each bandit step to the top or to the bottom. Okay, now we've done with all the complex stuff. Let's get into evaluation and key results. The simulation methodology, we've actually used 2 different simulators. For data prefetching, we have used Chatsim, which is a trace-driven simulator for data prefetching. And for Gen V5, we've used the execution-driven simulator. Oh, it actually says here 5 state-of-the-art prefetchers, I guess. It's actually 4. I think that's a problem from the slides that I sent to John. And then here we evaluate against simply instruction count and the choice list that I presented to you, the unchanged. Okay, so here on the X we can see the different workloads, and then here on the Y-axis we can see the geometric mean instructions per cycle normalized if you would have no L2 prefetcher. And if you look at the nice part of this I move here, you remove all combination here to the right, we can see that Bandit actually seems to perform slightly better than Lydia and actually performs better than every other baseline option that we have. So Bandit outperforms simple stride option by 9%, Bingo by 2.6%, MLOP by 2.3%, and Pythia by 0.2%. Note that all of these workloads are single core workloads. So if we go to multi-core workloads, I think in this experiment they have been used 4 cores, then we'll see that Bandit outperforms stride by 6, Bingo by 4, and MLOP by 2.4%. And Bandit performs worse than actually Pythia by 0.2% for multi-cores. And there is a reason given in the paper, but basically is that the reward becomes more noisy and it's difficult for the 4 different bandits without communication to decide what a good or what a bad action is. Okay, so now we come to instruction fetching. And here we can see the number of cycles in percentage. And here we can different events, we could basically say. Here we see the number of cycles where we stall because the reorder buffer is full. Here we see the number of cycles we stall because the instruction queue is full. And what we can see here is very interesting at the store queue, which shows that we actually have a reduction in cycles stalled, which comes from removing this antisymmetric fetch gating that I talked before. And in total, this means that we reduce the fraction of stalled cycles by eliminating conservative fetch gating, and we outperform the choice policy by 2.2% and the sold instruction count by 7%. Okay, now we've done a lot. Let's come to the conclusion. We introduced Microarchitecture, a reinforcement learning agent based on multi-armed bandit algorithms that is lightweight and reusable. The contributions, we've done many, but first one is the temporal hygienity in the action space. The second one is that we've shown that one can adapt multi-armed bandits as an efficient and reusable learning mechanism for such problems. The third one is that we implemented an RL agent using discounted upper confidence bound. Fourth one being we have provided simulation-based evaluation for 2 problem domains. And then we have also customized the choice policy regarding fetch priority and fetch gating. We have just seen the evaluations, but basically it's good to see that we outperform non-real prefetchers and attain similar performance to reinforcement prefetch Pythia by imposing a significantly lower storage requirement of only 100 bytes per system. Yeah, and also for instruction fetching, we outperform the policy by 2.2%. Okay, this is just a general structure question. Should I continue with the critical analysis and discussion, or? Should I decide myself?
Yeah, there is no more question.
Okay, oh, yes. I was just very, yeah.
Just checking out, can we go back to slide
24, or you even remember the slide, that's good. Okay.
What's the difference between RRD 1 and 2 since the strike re-entry when we go 0? Why would
1 and 2?
Yes.
The next slide.
Okay.
Prefetcher. So this is basically no prefetcher.
I see.
Yeah, okay. No worries. I mean, that's why I'm here for. Any other questions? I hope the problem was not that no one understood what I was trying to tell you, but okay then. Thank you very much for this feedback. Let's move to the strengths. I'll have to skip a little bit. Okay, let's move to the critical analysis. So first of all, the positive things, the strengths. This paper addresses real-world challenges of reinforcement learning in computer architecture. I've talked about it. For most problems, we have high complexity and storage overhead and limited reusability. Also, if you remember I think 2 weeks ago, actually, when Sybil was presented in the paper, Rakesh said that even integrating, for example, migration policies, Victor, I think that was your question, if I'm not wrong, that integrating migration and eviction policies from the 2 storage devices might be quite hard. Whereas if we would have microarchitecture, obviously integrating new functionality is easier than before. On the second part is, now I've talked a bit too much, it's easy integrable with different computer architectural decision-making problems. We have shown it on 2 problems, on instruction fetching and data prefetching, but there may be many more, which we're also going to discuss later, that MAB might be applicable to. The third part is it's evaluated on multiple different configurations cache level hierarchies, etc., on multiple problem domains, and also various different traces. So we can be sure that the author of the paper has, in that sense, done their homework. And the 4 is the one that I talked about, is in fact exploration analysis of different MAB algorithms. For these kind of algorithms, it's often that either we completely always explore the whole state space, meaning that, I mean, we never converge to a solution, but we simply try or oscillate between different solutions that never really are the optimal, or in some cases, we even pick one solution from beginning to start, and then we say, oh, look, we have this and that performance, while our program has actually done nothing. So an exploration analysis is good to show that your program actually reacts to changes in the workload, and then also chooses not maybe the most optimal, but one of the best performing policies or prefetches in that sense. Okay, and now let's get to the next step, the weaknesses. The largest weakness in this paper is this aspect of temporal homogeneity. First, we need to address that it might be that temporal homogeneity, as we've seen in the paper, it oscillates by quite a lot. We have seen some workloads where the first action repeated is very, very high, or we've seen some workloads where the first action that we basically tracked was very, very low, if you remember the graphic. And it might be that for unseen workloads that we have not tested in real-world life scenarios, temporal homogeneity is not that big as we would think. So logically, or micro-independent would perform quite worse. The second one is actually even more drastic, probably, and it's about the analysis of temporal homogeneity in the prefetching case. We have seen that the paper simply has presented an analysis where we say, okay, look at Pythia or state-of-the-art prefetcher, and then we check how often this action is repeated. But in general, this does not mean that the actual problem space is temporal homogeneous. It just means that Pythia makes temporal homogeneous, I guess temporal homogeneous is the best way, decisions. So it might be that what Pythia is doing is actually wrong. There may be better approaches that we are unable to find because we're only focusing on this analysis of Pythia. It might, actually not it might, but I think personally it's crucial that one needs to include a motivation or analysis rather on how temporal homogeneous, not only the tool is Pythia that we're working with, but rather on how the real problem domain underlying it is. I hope that made sense. That was a very long sentence. Okay, perfect. Then let's come to the next weakness. I've already talked about this, but the true algorithm exhibits non-adaptive features for instruction fetching. For example, these thresholds. I said these thresholds are set by hill climbing, but that's also not necessarily optimal because every time we change the structures that we are monitoring, basically, it might be difficult to convey the last thresholds that we've seen to the current thresholds. So finding a way to either integrate them in some sense into the agent or finding different ways might actually be worth looking into. And the third part is the hyperparameter. I mean, hill climbing and also MAB uses hyperparameters for exploration exploitation. So it would be very important to check that for unseen workloads, this actually holds. And I guess, I mean, it's important to say this is a problem of many ML applications that hyperparameter is always very critical and important. Okay, so that would be my analysis on the paper. I hope that when there are still no questions, it's not my turn anymore, but your turn. Okay, perfect. I will continue. The first discussion point. I know this sounds very broad, but machine learning in computer architecture. I believe Professor Mutlu has published the first paper about reinforcement learning in computer architecture in 2008, when he was working at Google in, I believe, San Francisco or something like that. And is it wrong, Mohammed? You're looking at me like it's wrong.
Yeah, Microsoft.
Oh, was he at Microsoft? Okay, then I am very sorry. I don't want to lie to you, but when he was at Microsoft. And since then, this research group and other research groups has also worked on reinforcement learning in computer architecture. Actually, there's a very nice graph, statistic graph that we see. Here on the x-axis, we see years. I think it's always 3 years. Yeah, it's always 3 years. On the y-axis is paper count of papers for AI in computer architecture. So reinforcement learning, computer architecture, etc., etc. And we can see that the trend is rising very much. We don't even include papers from 2019 to 2024. So I guess you could say the trend is still ongoing. But the big question is that industry is still quite hesitant to implement, for example, reinforcement learning prefetchers and also different kind of proposed papers into their tools. And then the question obviously becomes why. And to a little bit dig deeper into this question, I have brought some discussion points here. You can see 4 discussion points here. And what I want to do in the following, I want you to pick one of the discussion points, 1, 2, 3, or 4, and maybe give a short outline or short discussion on, from your part, what you think is the problem or what you think hinders or maybe also motivates ML for computer architecture. I hope that makes sense. I will just wait a minute to make any actions. And if then no one's still reacting, then I'm going to try explain or maybe give an example or something. So thank you very much. Okay. So just think very hard now. Everyone is supposed to think very hard. Very hard thinking. You're not thinking very hard, you're laughing. Very hard thinking now. And yeah, I'm not that type of teaching assistant normally, but if no one raises their hand, I will have to call up someone. It's just for my personal sake here.
I'll get started.
Oh, Jan, thank you so much. Okay.
How did you count the number of papers?
I didn't. That's a statistic that was provided by someone else. But we are not at the question part anymore. We are currently at the thinking very hard part. Thanks very much.
I have asked this. So,
okay.
How do you know that the industry doesn't implement ML techniques in their?
No. It's what I said is wrong in that sense. Is they obviously implement ML techniques, but what I mean to say is that most of, and this is from doctor students I talk to, that most companies are actually hesitant to do like a lot of the computer architecture techniques for ML because of points that are here on the slide and that we might want to discuss now. So do you understand what I mean? I know that industry is actually doing it and there are use cases where it's actually quite useful and important, but in a more general sense. I mean, one could say, why don't we have one reinforcement agent for the whole storage system or for the whole, no matter where you're working. I don't think it has an application of RowHammer, so it's difficult. Okay. 20 seconds, let's give 20 seconds to think. Look, I really don't want to be the guy, but Victor, let's maybe have you. Oh, you're about to, right? Look, how lucky.
I guess like it's maybe about complexity or probably.
About what?
Complexity, like the first one that you have. So like in general, it seems more complicated than what is already being done in the hardware right now. And so isn't it just like difficult to implement? Doesn't like take time to implement this, even though it's maybe done in research, but if you want to do it in production, we need to maybe a bit more testing and research, but they wouldn't maybe explain why companies are hesitant and like look into it.
I mean, as we said, Atterberg already said that obviously some companies work on ML for computer architecture, etc. But you're actually completely right. I mean, computer architecture for also a lot of use cases tries to be cheap. So not cheap in the sense that we want to do that we want to give garbage out to the people, but cheap in the sense that obviously we have profit in mind. And we have heuristics that work quite well for simple methods that have been developed for decades and decades. And we know that these perform very, very good. And for most use cases, these slight, you could say, improvements of, improvements in, for example, prefetching, etc., is, as far as I understand, not worth the company of doing like some brief development, testing, and then shipping out and everything. So basically, it's just a profit thing in that sense. thank you very much for this point. Yeah. Yes.
As you said, the motivation of this paper that we can't generalize the analytics for different applications. So I guess that's the major factor because all types of applications run on the system, and it is very difficult to design like one for all.
Yeah, definitely, definitely, I agree. I mean, also one has to decide very clearly, as you said, which agent to have where, basically where you get the most benefit of it, and also require a lot of analysis. And obviously, proposing something in a paper here or proposing something as Civil had done is quite nice, but to be shipped out into industry and to be able to work with it is actually quite difficult. Okay, I think this is fine. I think this is fine for. Oh my God, we have a third person. It's crazy.
Maybe I think it's the fourth point. Why? Because so in the analysis, what we do is we provide performance improvement in a lot of things. But for specifically deploying purposes, I mean, many of us know that most of the companies, they have a huge verification team, and that's what they do. So in the sense that we go at the RTL design level also, once we design the architecture in hardware, there are no test bench yet involved, I believe, that can actually check it. So let's say we have like for general architecture, we can do some testing of the circuits, like by performing design for testing, verification, and another formal functional verification. But still, like, lot of faults are being figured out in floating point units because it's quite difficult to do it in floating point units. The verification, you cannot achieve 100% coverage. And for these techniques, I think they are not evolved yet. So I think companies might be resistant to do this. Once you should have a proper test bench also on how can you impose all the input values, all zeros and ones to the circuit, and then verify that it's working fine for every corner.
Yeah. By the way, I finished.
Yes.
Yeah. Thank you. Really. Thank you. It's kind of too hierarchy that when we actually try to add this actually into the industry streamline, we need to invest a lot of money, a lot of resources, a lot of manpower to actually build that systems. You can test this, you can validate this really good. So thank you very much. Actually, 3 people is enough. That's perfect. So let's move to the next point, which is, I mean, I think that's a little bit clear. Looking at other problem domains that we have in microarchitecture, which others could be modeled using reinforcement learning, specifically these multi-armed bandits that we talked about, that might potentially exhibit some temporal homogeneity. By the way, now it's important for you to know that I don't expect you to have numbers off the head, but just take a valid guess. Like, nothing is wrong here. Just try to think of some. Okay, I just wanted to give you a hint, but I'm not giving you a hint yet. Just try to think of some problem domains that could be modeled using reinforcement learning, and then try to think about the next step. Oh, might it be that this problem domain actually exhibits temporal homogeneity? I will again give you a minute of deep thinking. Yeah, and if you have any idea, just raise your hand. $30 seconds.
Pretty hard to find.
I'm like counting.
Maybe you can remind what temporal homogeneity was.
Obviously, yes. Okay, let's do the following. Wait. Oh, wait. Someone asked in the chat, is the voice low for everyone? For 36 minutes ago. Thank you for telling me, everyone. Wait, you're making me share C. Wait, I'll have to do it this way. You didn't see anything. Yeah, I mean, temporal homogeneity of the access space is what I described here on the down left picture. Is basically that doing an RL episodes, meaning while we're communicating with the environment, we have one action that is repeated multiple times. So for example, in prefetching, it would be if you have a huge loop, and then we prefetch always the next few elements in the access key. For instance, that is temporal homogeneity. And now I'll just move back. I hope this is a good enough reminder for everyone. Let's move to the second discussion point, which is basically which problem domains in general could be solved using reinforcement learning. You can also talk about RL problem formulations, papers that you've already seen in the past from different presenters, for example, for 2 weeks, and then think about if these problem domains might exhibit temporal homogeneity. Again, I will just give you a little bit of time to discuss with yourselves or to take a quick think. It's a difficult problem. Is this raising your hand? Okay. Okay.
I am not sure. Maybe possibly can we predict the data dependencies in the instruction flows using the reinforcement? Just like what out of order execution does, instead of that, and we replace it with a RL agent in which we can access. Maybe we find out what is the register accesses that we are doing, and then can we predict?
That's actually a very nice question, and I have to make a quick think.
I don't know if it's in the solutions that we are sure. Possibly that can be do.
Yeah. I mean, there I would actually see a big problem, or not a big problem, but my first concern would be that it might be very difficult to find this aspect of temporal homogeneity. To be honest, I'm not an expert on order execution, and I don't know. Wait, let me think. So I think you could potentially model it as a reinforcement learning, I guess, but then it might be that you have to have many arms to model the relationships, if that makes sense, what I'm saying too.
So, okay, so in out of order execution, we do some sort of register renaming.
Yes.
And
exactly.
there is some algorithm which is possible. I don't know how efficient it is because I don't
Yeah,
know the
exactly.
exact algorithm also.
Yeah.
But if we can specify like okay the access pattern and can we make the instruction reordering more efficient using not RL also but any machine learning technique. So that they properly execute or maybe the processor don't stall or perform less stalls by efficiently executing out of order. I don't know if compiler already does this to the max extent that they do that.
Yeah.
But
Yeah, to be honest, it would be good to know actually what the compiler does in that sense before thinking about it.
yeah, exactly. I don't know.
Yeah.
If compiler does it, can we put this thing in compiler or it's better to put it in the microarchitecture so that it's efficient?
Yeah, it might. I mean, the problem with compilers that I see is that, I mean, especially for applications that need to be very, very quick, compilers are designed to be extremely fast, right? For example, in the banking industry or etc., compilers have to be very fast. And I'm not sure how quick we would be if we would have to include.
Also, actually, we don't know the value or the input before that while executing it. So compiler will not know exact values also, what exactly they need to maybe.
Yeah, actually that sounds interesting, but I'm not totally sure about that direction. But thank you very, very much for the contribution. You're smiling very much.
Maybe we can use it for tasks anything.
Yeah, definitely. I think actually I'm not gonna say anything about Professor Mutlu's paper anymore in at Microsoft in America because it might be wrong, but I think his first work was regarding scheduling in memory, right?
Memory control.
Yeah, memory. Okay. Forget that I said anything. But yes, exactly. Thank you. I'll just wrote down some stuff that I wrote. I mean, on the cache and pre-cache we already talked about a lot. In general, schedulers and controllers, in my opinion, where reinforcement learning works quite well. For instance, also inside SSD or inside storage, there are multiple resources that we need to allocate fairly, that we need to allocate quickly, and it might be important to, or might be possible to build RowHammer agents that actually take over this kind of communication between different parts of architecture. And the third part is branch prediction. I thought it might be possible that for a lot of branches in the program that we take, we actually take simple actions that might be not possible. I'm not an expert in branch prediction, but that was just my thoughts and my beliefs on the topic. Okay, so let's go to 3. What security vulnerability could ML-based approaches lead to in microarchitecture? We have already talked about complexity and about how we would implement and test it, but now I want to know about concrete security vulnerability approaches that ML applications exhibit. If you have any idea, please raise your hand. Again, I will give you like a quick thing. And you can, again, also think about other presentations about reinforcement learning for complete architecture that you have seen.
So do you have some thoughts, initial thoughts?
Yes, but that's kind of my solution. Like the next slide would be my initial thoughts on the topic. But I can also talk about them now, and then everyone can chime in.
Yeah, maybe it's better that you give some initial.
Okay, then let's say the following.
Starters.
Okay, I'll give some slides. But at this point is just like this, because we have had some similar point 2 weeks ago in the presentation where hopefully everyone was watching and looking into Sybil. Yeah, but let me give my first thoughts. So, I mean, security vulnerability can mean a lot of things, but what I envisioned in the first when I thought about this, since we use online reinforcement learning, this means we are learning from data that is constantly coming in. Now the problem becomes, let's say I'm an attacker that wants to hurt the system. Now I can try to make access, or try to make false patterns that actually, or my multi-arm Bandit performs worse, meaning that I learn patterns or I learn relationships that are actually not true for normal data, meaning in the whole system, I actually perform way, way worse than I would have without this ML-based approach. This is a big, big problem for many ML-based approaches and also for online reinforcement approaches. And although there are some solutions that I'm going to quickly scrape at, it is not totally fixed, not totally resolved in that sense.
And the problem that you said, that would be during the training phase, right?
I mean, since we do online learning, there's not necessarily a training phase, right? So at the whole point, the RL agent is running during the whole episode. At some point, I could come in and then force the MAB algorithm to kind of pick wrong because my attacks are just because my requests are very, very much. So it worsens the performance. And what we've actually seen, and that's very drastic, is that for the choice policy that we've shown, that picking the wrong policy actually can reduce the performance by 30, 40%, which I mean is insane. It's insane that okay, so given
Like if it's an online learning, then there can be a lot of attacks because attackers can post some data to come with the shared resources like names or caches and then get their data by using it.
Yeah, exactly. Thank you. Yeah, otherwise I'll just make a quick show. As you said, no. service attacks. I mean, we have malicious workloads that work with malware compared to real workloads where we then the wrong patterns. And there are also solutions. I mean, we can limit the changes in each thread, in each iteration of the Bandit that we basically can do, so that even if we occur against some of these attacks, they do not influence us as much as we would think. But also, they might not work for workloads with large variations. So this is not a very good fix, but there is still a lot of work to be done here that hopefully that will enable also a very solid security of the whole system. Yes, that is everything from my side. Perfect. Okay, this is everything from my side. I have to thank you very, very much for your attendance, first of all, and then for being silent and listening to my presentation. Thanks a lot to the people who contributed to the discussion. Yeah, thank you. Have a great day.
So, Rahul, do you have something to add?
Oh, can you hear me? Sorry.
Maybe you can ask.
Hello, Rahul?
We can hear you.
Who is not here?
Hello?
Can you hear me?
Yes. Wait, is that
Okay. Rahul is not here because he needed to attend another meeting.
okay.
I can make the final comment if you want.
Please.
Yes, so the presentation was good. Thanks for the presentation. I guess this problem of like either, the last point you discussed, how to, what are the sort of attacks are coming up because of ML, or what sort of attacks we can detect because of ML, or what sort of attacks we can basically prevent because of ML, is an emerging, I believe, topic in computer architecture. There are also a couple of works on that from Daniel Jimenez's group, I think. With respect to the paper you presented, I think it's a clean idea with respect to, I think that the core concept is what you described, that they're trying to basically do some sort of distillation. They're trying to shrink the model. Given the fact that Pythia's action space, as you mentioned in your weakness, is pretty, let's say, boring and temporally homogeneous. I guess, as we have discussed with Rahul also internally, for workloads that need more complex behavior and you don't have this sort of temporal homogeneity, or workloads that, for example, would work really well with indirect memory accesses and indirect prefetcher, for example, this would definitely not work. So yes, I think this is the key weakness of the paper. And I agree with you that this can also be extended to other sort of microarchitecture solutions and basically shrink down the models in case there is temporal homogeneity. That's it from my side, if you want to add anything.
Thank you, Konstantinos. Thank you very much. Also, thank you for listening. I am sorry, apparently my voice was very low. I was not aware.
No, it was not. For me, it's fine.
Okay. That's great. Not everyone had the same
problem. It was slightly low, but it's okay.
Okay, perfect. Then at least you had to hear a little bit. Thanks for the feedback, by the way. Yes, to be honest, I also think that, to be honest, the first time I read the paper, I thought it was not a bad idea, but I was worried about different workloads, more complex workloads in that sense. And I agree with you that there are definitely cases where this kind of idea fails, but I think it's a nice and basically you could say simple idea on trying to lower storage requirement and increase the reusability, as I already said. Yeah, so yes. Thanks very much. Again, I guess this is the last time I'm saying this. Thanks very much. And now good luck to my other guy, to my friend Victor, who is not.
Thanks, Talu.
But yeah, thank you. Who will be presenting shortly.
Okay.
You're doing it. Okay, perfect.
Now that I think about it, it's impossible to actually verify chips quickly. Because in your case, you don't really know it's so we cannot really ideally you want to the reinforcement that we're teaching something but not expecting to do. Yeah, that's
Maybe I don't know if you can break the full circuit policies, let's say and or gates, and then try to retrieve the values. Yeah, but at a system level.
Like what type of food did you eat in Boston? See? Have you tried the Boston one yourself? I'm so curious because I always see the pictures and I always ask myself how it tastes. That's a question. How was the food there?
Depending on the time it was, the seafood was
Depending on the time. I mean, if you go eat something at 2 a.m., 3 a.m. in the morning, it's difficult to find good places.
So are you going to stay here mostly? Because I followed it because I then placed the microphone accordingly. So that,
Yeah, I think.
okay, so you can take a look at the camera here to see like how it looks right. If you want to position.
Right, okay. Yeah.
And you pronounce your name as Victor or Victor?
Victor.
Victor. Mohammed, are we having a break or getting started now? Okay. And, hello everyone, welcome to the second paper presentation today. Victor, who is in his sixth semester and he's doing his bachelor's in computer science, who is also going to start his master's also very soon. Is going to present this GMX paper. This paper was presented at Micro last year, and this is a bit on the direction of bioinformatics and genome analysis, which we also covered this direction in the seminar course a few weeks ago. So yeah, Victor, please take it away.
Thank you very much for the introduction. You've already said some of the very basics about the paper. So this paper really tries to address some of the core deficiencies that the current approaches for genome sequence alignment have. Just a very brief summary of the paper and my talk. Genome analysis is very useful for many applications in modern biology, but unfortunately, it's currently bottlenecked by the sheer amount of compute that it requires. And the current approaches that we have of implementing it are usually either too slow or they are too rigid, too inadaptable. They are just like domain-specific architectures which are designed for just one very specific problem and can't be used for other ones. This is where GMX, this paper, comes to the rescue, which comes with this novel idea of extending an existing processor ISA with instructions that are very efficient at processing these tasks. And it indeed delivers on much of these promises. It is much faster than the software solutions that the existing software solutions. And at the same time, it's much more adaptable than the existing DSA, domain-specific architecture solutions that we have right now. This is a very basic outline of my talk. In the first 5 sections, I will focus on the actual content of the paper itself. And at the end, I will try to do some of my own critical analysis of the paper, what I think. Well, let's start with the background. Genome analysis. Well, what a genome is, it really contains all the necessary information about how a living organism functions. So by studying the genome, we can gain very deep insights about the organism or about biology. It enables us to develop personalized medicine, to estimate the relative abundance of microbes in samples. It enables us to track the advances of infectious outbreaks, or it allows us to study the genetic traits of humans. In reality, a genome is a set of polymers consisting of organic molecules, but for us, what's important is that formally we can look at the genome as a word over a 4-element alphabet, where these elements are usually denoted by the letters A, C, G, and T. The genome analysis comes with an entire complicated pipeline. There are many steps. You have to collect a sample, you have to convert it to the kind of string that I've just shown you, and at the end you have to interpret the results meaningfully. But what we want to focus on in this talk, and what the paper focuses on, is this sequence alignment step, where you have 2 sequences. You have the sequence that you've just read from the sample, and you have some reference sequence that is what you're kind of expecting to see. And you have to align them, you have to compare them and see how similar they are, and where and how they differ. In particular, when you talk about sequence alignment, what we specifically want to know is that given 2 sequences, we are looking for a minimal set of individual edits of characters that take us from one sequence to the other. For example, to get from the word Netherlands to the word Switzerland, you can see that there are 5 of these edits necessary. In other words, you can also say that there is the edit distance of these 2 sequences is equal to 5. Anyway, how do we compute the edit distance in practice? There's a well-known dynamic programming algorithm for this, which uses a 2D DP table. Each element of the DP table is the edit distance of the corresponding prefixes of the 2 strings so far. And each element can be computed based on whether the 2 corresponding characters are equal and based on the 3 neighbors to on the top, to the left, and the top left of the cell that we are computing. This way, with these dependencies and this information, we can compute the edit distance by computing the entire DP table. This is the exact formula that is used for this computation. And once we compute the DP table, we can read out the edit distance at the bottom right. We can also trace back through the DP table to read out the specific edits that we need to convert the one sequence to the other, which is shown in the middle. And at the end, those are exactly the necessary edits that convert these 2 genomic sequences into each other. So what I've shown is really the classical DP algorithm, which does that, which uses, for strings of length n and m, uses an n by n DP table. And it should be hopefully clear that this needs n memory and time. But this is also a basis for many other slightly different variations of similar algorithms. In particular, there are so-called bit parallel techniques algorithms, which also solve the same problem. And what the insight there is that they try to use as many bitwise operations in the implementation, which takes advantage of the fact that these operations are implemented very efficiently in hardware, so the entire algorithm can be fast. Specifically, the GMX paper uses a variant of the so-called Myers algorithm, which takes advantage of the fact that in the DP table, the difference between any two neighboring cells is, or the absolute difference between the two neighboring cells is always at most 1. So we can reformulate the entire DP and compute the entire DP just in terms of these cell-to-cell differences instead of the actual values, which has the advantage that the cell values are now bounded to be just 2 bit numbers between -1 and 1 instead of being arbitrarily unbounded integers. And so that can be more efficient. But however, that's still an M by N time and memory algorithm. It's just faster by some constant, but that's already very important. Here you can see the original DP table can be converted to this difference DP, and the formula for the new DP in terms of the differences can be derived quite simply by some algebraic manipulation by substituting the definition of these differences into the original DP formula. There are also some other modifications that we can make to the algorithms to make them either faster or more accurate based on some specific insight into the domain that we are using them in. We can, for example, find approximate solutions by computing just part of the DP table, which is obviously faster, but doesn't guarantee that we find the best solution. And we can also adjust the cost function of the alignments. We can, for example, set different penalties, different costs for the different kinds of modifications that we make. Or we can use so-called gap-defined scoring, which basically penalizes a sequence of edits less if they appear contiguously in one of the strings. And these two approaches both can be can give more accurate results in practice in applications such as genome alignment. And generally, they are still can be solved by theta and TPs, but they are by some constant more computation expensive. And also, this single-cell alignment also has other applications, such as in information retrieval or natural language processing, just so that you're aware. However, the problem with current approaches is that in genome analysis is that in recent years, really the genome sequences have gotten much faster, and they produce much more and more data, and the genome analysis tools processing has not been able to keep up. And one of the problems is that the algorithms are quadratic, which just doesn't scale so well. And so much research has been invested into finding better implementations, more efficient ones. And right now, the solutions with the highest throughput are really these domain-specific architectures, which are always designed to solve like specific, mostly narrowly defined problem, and it's hard to reuse them for other problems. Another problem is high memory bandwidth and usage of the existing solutions. Often memory can become a bottleneck in the existing solutions. And specifically for the software approaches, the problem is usually that they are just too slow. They have low throughput. They just don't provide enough compute to be competitive. And the DSA solutions, as I already explained, just have limited applicability to other similar problems. And they can be quite expensive. You just need to design a new DSA for every problem. So how does GMX try to address many of these issues? The core idea behind, so GMX stands for Genome Alignment Extensions. And the core idea is to extend an ISA, the instruction set architecture, of an existing CPU with specific instructions which allow the computation of not just one element in the DP table, but an entire tile of many elements in the DP table by just one instruction. And this can be fast because the implementation of this instruction can be made very efficient in hardware by adapting the Myers algorithm. That's the one with the differences that I've shown. We are able to efficiently implement this using clever bitwise operations in the hardware, and therefore simply the entire computation can be quite efficient. Just a very quick note about RISC-V, because the GMX is an extension to RISC-V. So in case you're not familiar, RISC-V is different from other ISAs in that it's an open standard, and it makes it much more accessible to do research, especially academic research, into architecture, into CPU architecture, such as in this paper or in many other papers. It's much more easy to build upon, for example, research in this paper thanks to using this open ISA. I've divided the overview of GMX that I'm going to present into multiple sections. And first, let's look at the high-level principles of high-level algorithm, how the GMX instructions are used to compute the entire DP table. As I said, the table is computed using square tiles of T by T elements. This number T, for the purposes of our general instruction now, is just some arbitrary number. However, in any concrete hardware implementation, it will be a fixed integer. One key insight that the extension that GMX comes up with is that when you want to compute the elements in one tile, the only elements outside of the tile on which this depends are the edge elements of the other tiles. What that means is that while computing the DP table, you don't need to store the internal elements of each tile. You can only store the edge elements, because only those are needed for the computation of the remaining tiles. And that obviously saves a lot of memory and memory volume, but also memory bandwidth. And this is a diagram of how it can look more concretely. When you want to compute one of these tiles, what you start with is a vector of T elements of these delta V values, in this case, on top of the tile, and a vector of T of these delta H values, in this case, on the left side of the tile. These are both inputs to the instruction. The instruction also looks at two architectural state registers, which are part of the ISA, called pattern and text, which contain the relevant slices of the two sequences that you are trying to align. And it takes all of this together, and it spits out the delta V, the T values of delta V, in this case, at the bottom of the tile. And there's a similar instruction which computes the delta H values at the other side of the tile. As I said, there are these two instructions which compute the delta V and delta H values in kind of the forward computation of the table. And there's one more instruction which is for so-called traceback, when you want to when you've already computed the DP table and you want to extract the precise sequence of edits of the operation that you need to do to get from one sequence to the other, you need to trace back through the DP table. That's for the last instructions part. Other than that, there are just 5 registers which the extension adds to the overall ISA. And so how is this actually implemented in the microarchitecture? The core addition that this extension makes to microarchitecture are these two modules, this GMX AC module, which is used for the computation of the delta V and delta H values, and the GMX DB module, which implements the GMX DB instruction. each of them consists of a T by T grid of these smaller submodules, which themselves have some implementation. And each of these submodules then kind of indirectly corresponds to one element of the DB tail that you are ultimately computing. And I want to focus on the implementation of the GMX AC, each of the GMX AC module submodules. What they need to do is to compute the delta V and delta H values according to this formula. So how do they do that? They one thing that you notice is that the formulas are quite similar. So we can factor out this GMX delta function, which is kind of the form of the entire formula in both cases. And each of the formulas is then just the GMX delta function just called or evaluated with the arguments in a slightly different order. What that means is that each of the GMX AC submodules consists mostly of just two copies of the GMX of an hardware implementation of the GMX delta function for different orders of the arguments, but otherwise that's it. And how do you compute the GMX delta function? For that, we just need some meaningful encoding of the delta values, which again, from how the algorithm works, are always just 1, 0, or -1. We can therefore encode them into bits. And it turns out the GMX delta function can just be computed by this formula, which you can check by exhaustively trying all the inputs. What's important is that this formula is actually just a relatively short sequence of bit operations, so it can be implemented very quickly in hardware. One technical point that comes up when implementing this in hardware is that even though the implementation is sufficient, it is still quite large if you compute the entire module, and it is not usually possible to compute it entirely in one cycle, in one CPU cycle. So you need to, especially when the T is high, so when the entire module is large, you have to segment it into several cycles. In order to do that, I think that's quite intuitive. You just need to insert registers instead to save the state along several anti-diagonals in the grid, because you are computing the elements from the top left to the bottom right. This is especially the case for the GMX DB module, because it has to do a bit more computation. The critical path is longer, so there's a high latency of the entire module, therefore needs more cycles to execute. But the good news is that as you increase T, the latency grows, but only linearly in T, whereas the elements that are computed by the entire module grow quadratically with T. So when you increase T, you can increase the throughput of the entire system, even though the latency of one module is getting larger. So what about the complete measurements? What about the complete results that we get for a specific implementation of this? Before I really give you numbers, and there's some important information I think we should say about how this was implemented. So what was done is the authors extended the microarchitecture of a 64-bit Linux-capable processor with an RTL-based design, and I think that the most important decision is how we choose the value of T, which is the size of the tile that you compute by one instruction. The first consideration is that that the inputs and outputs of the instructions, which are these vectors of length T of the elements, should fit into one machine word register. And since each element can be encoded in 2 bits, t times 2 bits should not exceed 64 bits, which is the size of the register. And the second consideration is that larger values of t give you larger throughput. So given these 2 principles, it seems optimal to choose just t equals 32, which already leads to over 1,000 elements computed in each child. And to fit into the 1 gigahertz frequency of the processor, the authors needed to segment the AC module into 2 cycles, the TB module into 6 cycles. I would say the most important metric here is the throughput of the implementation, which you can see compared here. So here is a comparison of GMX versus the state-of-the-art software implementations. On the y-axis, there is the throughput, the alignments per second. On the x-axis, there are various different selected sequence lengths that are being aligned. And the different colors correspond to different approximations that are done during the computation. So the yellow and green ones are where you compute the entire DP table, and the other ones are where you just compute one or the other part of the DP table. And well, in general, GMX outperforms the software solutions by relatively large margins. In particular, for the short sequences, it's at the lowest point, it's 18-fold, but in some cases, it goes into the hundreds or thousands. And similarly for the long sequences, where it's 42 times or more. And one thing that I think I should mention is that for the GenAsym approach, that's something that was not intended really to be executed on a CPU. So in that case, the comparison is maybe not completely fair, but the other ones I think should be fair. And this is a comparison against the state-of-the-art DSA solutions. Here you can see that the difference margins are much smaller, but still GMX is slightly faster, has slightly more throughput. However, I think it so what I should point out is that it is faster here, but if you consider the throughput per area, then GMX actually performs slightly worse than the DSAs. But what I think is fair to say is that it has a somewhat comparable throughput as the state-of-the-art DSA solutions. And what about the memory use? At the bottom, you can see memory bandwidth used by the different solutions. And on the top, you see, which is related, the relative speed up that you get when you increase the number of CPU cores that you are using in your system. For example, for the green line, which is not GMX, you see that as the bandwidth, when the bandwidth gets large, for example, for 10 kilobase points, you then get in the top right graph, you see that the speed up gets much worse than linear at 16 threads. But GMX manages to keep the bandwidth quite low, and correspondingly the speed ups stay almost linear, with the only exception of windowed GMX, where the amount of compute the amount of compute that you need to do per unit of data is actually very low. So you inevitably have to end up accessing a lot of memory in a short amount of time, and therefore the bandwidth is slightly higher and the speed up is slightly below linear, but still quite good. And the last metric is the the area and power, which you can see compared, or on in this table on the left, you can see the comparison of the areas of GMX and of other solutions. If we look only at the GMX modules themselves, which are added to the CPU, the area per processing unit is very low compared to the other solutions by a factor of 10 or more. But when we also include the entire CPU, or when we count everything, then it's about the same range, more or less as many of the other solutions. And here in the figure on the right, you can see in the bright green highlighted the area taken up by the GMX extension. And in the table next to it, you can see a comparison of the GMX extension with a 64-bit multiplier. And so what this is trying to show is that the area and power requirements of the GMX extension are roughly equivalent to just a few 64-bit multipliers, which is not bad, which is quite low. Indeed, the total area taken up by this entire extension is just around 2% of the entire chip area. Well, the slide's not working perfectly, but anyway, to conclude, the problem that we have and that we try to solve is that genome analysis is great. It has many applications, but sadly, it's very computationally expensive. And the current approaches are often either too slow or too expensive and too inflexible. GMX comes up with this quite new idea of extending an existing ISA with specialized instructions which can accelerate these tasks. And it implements these instructions in a hardware-friendly way in the microarchitecture, so that the entire process is fast. And it also has this innovation of reducing or battling the high memory use that is often associated with these tasks by just storing only a fraction of the entire DB table. And crucially, it is not limited to any one particular application, but it can be quite flexible. That can be used by any program that runs on the CPU that was extended with GMX. And the results support many of the claims. There is a high speed up compared to the existing software solutions, and the throughput is still quite comparable to the DSA solutions. The throughput per area is slower for GMX, but it's actually between a third or a half of the existing DSA solutions. There's a low overhead over the CPU microarchitecture that is being extended, and the memory footprint is so low enough so that we can maintain linear speedups all on multi-core setups. That's the end of the part that really focuses on the content of the paper itself. Are there any questions that anybody would like to ask? Sure, yes.
Thank you very much for the presentation, Victor. I just had a question to the evaluation where they showed for long reads up to 10,000 base pairs. I believe that's.
I think so. Yes.
Yes. Is this just their choice, or is there a reason why they don't pick longer reads? I assume probably they just tested it for 10,000, but maybe I thought they didn't show for 100,000 or something like that because performance is just much worse. Yes. But I don't assume, but it was just.
I think there is not a principal reason not to execute for longer sequences. I think this is just where they decided to call it a day.
Yeah.
Right. Anything else? So about how I try to analyze the paper. First, the strengths. I think the paper makes a good case of this being a new idea that wasn't explored that much in this field, that can lead to really a more flexible or more modular approach. Like specifically, in principle, you can take any existing CPU design and you can, or many different CPU designs, and you can extend them with this with these extensions. So you can so it's not one monolithic system. You can change the GMX extension, or you can change the CPU. It's a bit independent of each other. Also, this is related. There's the free choice of the parameter T, which makes it possible again to target different CPUs based on, you can trade off the area that you need with the throughput that you get. As I said, it's not exclusive to any applications specifically, and since they use RISC type, it's also, but this may be standard nowadays. It's open to further work, further improvements quite easily by further future research. The modifications that you need to make to the architecture are quite limited, which again is good, obviously. Both the area and the power consumptions of the GMX extension are, compared to this entire CPU, are very low. But even though the modification is this small, the throughput that this is able to generate, the increase in throughput, is quite impressive. Compared to, if you were to run an application of the CPU on its own without these extensions, it would be 100 times slower, maybe. And again, the memory footprint, it's not just about that the footprint is smaller, but also about the idea of how this can be done, that we actually maybe don't need to store the entire DB table, but only part of it. That's something that has good results, but it's also a good idea in principle. There are also obviously weaknesses that I found in the paper, or I think that they are weaknesses. I think the strongest point is that the paper claims this is an extension and it's quite general. It can be used by different applications, which is true, but it is still quite limited to one particular DB scheme. You can't really run any other DB scheme. For example, I mentioned previously the possibility of choosing different weights, different penalties for the different kinds of edits that you make in the sequences, and that's just not possible with this extension. It is also not possible to implement this gap-affine metrics, gap-affine alignment, which both of these could lead to more accuracy in the applications, but they are not supported by the extension, even though the extension claims to be general. Another point is, I think something to think about, if it's how good of an idea is it to really, do we need, since we are already making hardware changes anyway, is it a good idea to keep the entire CPU, even though in the genome analysis applications, we are going to spend most of the time in the GMX units anyway, and they take just 2% of the area? Isn't the rest of the area kind of wasted by things that we are using very little? Yes, that's nice. And there's one, I suppose, very technical point. I've shown there are these two instructions for computing the delta H values and the delta V values of each tile, and both of them kind of compute the entire, have to compute the entire tile, all the internal values, but we have to do it twice. Once, so they both compute everything, but each of them only returns only the delta H or only the data V values. So some of the computation is just being repeated unnecessarily, which can slow down this one part of the entire computation by a factor of 2. So that's the weaknesses of the paper. Now I have some discussion points. So my discussion points, I think, are a bit more focused on really the paper itself and maybe not as much on like general topics. Yes, but my first point is, I've mentioned it as my first weakness that GMX only supports the this one particular DB scheme. How is it possible, and if so, how and at what cost, to further extend the GMX extension to also allow other schemes? For example, allow the non-uniform costs for the different different edits or gap define alignment. If anybody has ideas about that, or I can start with what I thought.
So,
yes.
What do you mean by more general design programming schemes? How much?
Anything, actually, like, so the two cases that I had in mind were the non-uniform costs for insert, delete, modify, or the gap affine DP, which is usually formulated like with multiple DP tables, but it can be like reformulated with one DP table, but like a bigger state for each element.
Do you see any way of doing that by
Exactly. Not really. I think that's one of the main problems. Right. So, yeah, I think that's this point here. So Meyer's algorithm really, the core idea of Meyer's algorithm is really that the differences are between -1 and 1, and once you introduce in this case the non-uniform penalties, then you would start getting potentially much bigger differences between two cells, which would I think they would still be somehow bounded in like a linear way in the sizes of the penalties that you selected. So in principle, it might be possible to do something like this, to still have a bounded, to have the absolute differences between two cells, neighboring cells bounded, but it would definitely be more complicated, and it would not be between just -1 and 1. And in turn, that would mean that the difference can't be just 2 bits, it would be more, and would just decrease the efficiency of the entire system quite significantly, I think.
Like the insights of GMX, different algorithms that are biased.
So one can definitely try, but so what I think is that GMX definitely takes advantage of the fact that the state is really quite small, it's just 2 bits, and that's quite unique for Meyer's algorithm. So it's quite difficult to do that, or
So will it become, you think it will become too expensive of registered state, I guess, partner state?
I'm saying that if you, so you would have to expand if you have to have more bits per element. And I think there are like two options. So if you still want to fit into one machine register, you'd have just few elements. So the entire throughput would decrease, or you would have large registers, which is kind of changing the entire CPU architecture, or you would have to like pass multiple registers, which is complicated. So I think it's possible, but it works less well than GMX as it is. Yeah, unfortunately. Yes.
Yeah, I just want to add that this seems like a major problem for me of paper. I mean, obviously it seems nice on paper. I mean, finds a quick way of doing this normal analysis that we talked about, by the way, but not being able to change the gap find alignment or different weights for different operations.
Yeah.
Seems like actually extremely significant, because a lot of times you do different alignments and different kinds of readings that you get. I hope this is right, by the way, everything that I'm saying, John. Do you agree?
I follow partially, but
yeah, just from what like I've done, it's not like you don't always have this alignment. But
can you repeat?
I said that not being able to have different weights for basic insertion solutions or like gap closing seems like a major problem for me in this paper, because you usually or often also have like different alignment techniques that you want to use. That makes sense, right?
Implementation. I'm not sure if it's a huge issue.
Why is that an issue?
I mean, it's an issue, but I'm not sure if it's. Well, so perhaps it is a bit fundamental, right? You kind of fix it. But I'm not sure if it's really that much needed to be let's say, precise or tested around, because maybe all the algorithms have just been kind of very free. But so far we rarely have to trade off on these things. So or it wasn't really a choice. You spend the extra computation time for more complex. So it's kind of okay. Now you have the option, maybe you won't be considering, because actually it's not the benefit that you get out of the complex algorithms. Might be quite a little.
I think we've discussed part of it. For the gap assignment alignment, I think it's a similar. It's again, I think it would depend on the kind of if it's even possible to use something like Miles algorithm for this, which I think it might. I think the state would again depend on the state size for each element would depend on the somehow the ratio of the coefficients that you have in your gap alignment scoring. Do we have time, or when do we?
Just a bit more over the
yeah.
Maybe you can move on about it.
Yeah, yes. Okay, so my second discussion point is it's also related to my one of my weaknesses. What are the advantages? What are the disadvantages of basically doing this approach of keeping an entire CPU for something like a genome analysis application, given that we are making hardware changes to CPU anyway. Does that make sense? Are there any opinions on this?
I have a follow-up question.
Oh, sure.
Does your hardware design handle the full end-to-end genome analysis pipeline, or is it just handling part?
So it's only focusing on the sequence alignment part. So no, it doesn't do other stuff. Does that answer?
Yeah. Then I guess it makes sense to extend that into future CPU because other parts of the pipeline do the rest of the CPU.
Was that your point?
Yeah, I was wanting to say something similar. Always interesting.
Right. Yes, I agree. Yes. I think that's very related to what you said. So there can be a larger program which does other things, does other parts of the pipeline, for example, and everything can run on the one CPU. Yes, you don't have to need some kind of separate devices. Does anybody quickly have like an idea why is it bad, maybe, even in this case, or otherwise?
Perhaps that's also that if you can implement that is not beneficial to a genome analysis, it can be perhaps moved from the, like it becomes unnecessarily complex.
Yes, I think I was thinking something similar. So, I mean, yes. For example, there are other parts of the analysis, yes, of the pipeline that we need other CPU features for. But if the genome sequence alignment is really the bottleneck and takes most of the time, and so if you look at the entire pipeline, and really the vast majority of the time is being spent on in this one step of the genome sequence alignment, then it might be somewhat of a waste of area and power to have most of the rest of the CPU just sitting idle during this phase. And you could have maybe like a higher concentration of the actual GMX units to have like a more efficient ratio of the CPU area that you're using. That makes sense. Or yes.
Why are you saying there is a sequence behind? In GMX, yes, it uses almost all CPU hardware is somewhere, right? But by nature being simply an RSA extension, for example, all the caches, it uses the regular memory interface, and it uses the regular fetch decode RGM. So what's really being unused?
Right. Yes. Maybe it was an exaggeration to say that most of the CPU is sitting idle, but there are parts of the CPU which are not being used that much. I was thinking of units of the computation units for some operations that are not just not necessary at this point. I'm not entirely sure how much of the total CPU area and power they take up, but I think, for example, like some CPU operations or something like that would be non-insignificant.
I can still want CPU operations.
I mean, you can, but you don't need to when you're using the GMX cores all the time. Or
GMX just handles sequence. There's other tasks to be. So I can see a couple of things. I can either execute other non-sequence alignment tasks that are still part of genome analysis, or I could just complement GMX with hardware that's not dedicated to a function, but can still execute a function. Not like I can't use like SIMD hardware for design. It's just not quite effective as GMX.
So I'm not sure if yes, you can use SIMD for, like, if you have GMX, then you probably don't have reason to use SIMD for sequence alignment if you have GMX, right? Or,
why? Why not both at the same time?
or at the same time?
And certainly it's not as energy efficient, right? It's both, but you're still certainly your hardware doesn't go on this.
Okay. You could do that. It sounds definitely more complicated to orchestrate to somehow like to make it interoperable, like, because the algorithm, at least what I presented, kind of assumes that you do everything in GMX. If you somehow then start, if you want to start computing parts of the DB table using SIMD, it's probably possible, maybe not the easiest thing to do. And yes, you already said that it's like just less efficient. It would be, I suppose, more efficient to just have more GMX cores instead of trying to use SIMD, both for area, power, and things like that.
Yes, but at least it doesn't need to be on this. By the way, one convenient way of still using that cloud and to super fine grain cooperate between SIMD hardware and GMX here would be to use something like simultaneous instead.
Yeah.
So that's correct. CPUs and high percentage, right? So you always have ones that actually use the conventional hardware, ones that GMX work.
Yes, I think that's a valid point. Maybe if you had the choice, like, wouldn't it be worth if you could replace SIMD by another GMX core? I think, like, in total, this, if you sum it up, this would maybe end up like being more efficient. So that's maybe one thing that you could.
So you end up with more kind of an accelerated CPU than general purpose CPU with an accelerator.
But yes. Yeah, and what you do we still keep going? Okay, good. So this is my last discussion point, and actually I think we've already discussed parts of it. I think I'll just go through it. So yeah, we've literally talked about some of the things right now. How can we further increase the throughput of the GMX extension, or the CPU with the GMX extension? One thing one could do is to keep one CPU, the CPU core, and just add multiple GMX modules to it, which then you could have something like instruction level parallelism, where you could compute multiple. You could be computing multiple tiles of the DP at the same time, increasing throughput. In particular, you could either be computing, like, in one alignment task, you could be simultaneously be computing tiles along an anti-diagonal, or you could be analyzing two different sequences at the same time on one CPU core. This would increase the throughput per area, especially like compared to adding more CPU cores with just one GMX unit. Concentrating more GMX units on one core doesn't increase the area that much, but it increases the throughput a lot. So that would be a benefit. And the other option that one can think of, but is maybe not very practical, is try to make the GMX compute units larger, and particularly to increase the T parameter. And now, with at least with the setup that they had, they already use the entire 64-bit registers. So if you increase further, you don't fit into the register, and you either have to somehow pass the inputs and take the outputs in multiple registers, which is complicated. It probably again increases the area of the GMX implementation. Or you could change the register size, but that already changes kind of the entire CPU architecture. So that's probably also not a good idea. So this last point is something what we can think about, but not necessarily something very practical. So that's, if there are any questions or anything, I can answer them. But otherwise, that's everything that I have. Thank you for listening.
Yeah, maybe I can make some. I think that was a really nice presentation overall, especially discussion part. I like it. So I guess like many people actually touch upon this direction, but I guess so. Essentially, the way that I'm seeing these works is usually threefold. One is of course like algorithm design. Actually, one of the authors in this paper is as a contributor of this recent aligned algorithm WFA. So the algorithm is definitely changing. And the other directions are essentially should we basically design the domain-specific architectures, like we go with that direction, or should we share resources, right? And then design some hardware or CPU and so on. So I guess like all of these directions are valid and valuable in terms of research. But one basically doubt that I have regarding this direction that goes with the question or the point that, okay, why I want to share resources with the rest of the other applications and so on. And the question is like, what should be the abstraction level of basically your specialization in the hardware, right? Here, this paper takes the direction of, oh, I want to be specialized in the sequence alignment, so doing the deep operations for sequence alignment. But then the question is like, is this the right abstraction level? Because like we know that there are also these DP instructions that NVIDIA provides in their H100 GPU, right? And the question becomes, I guess, how much of the benefit that we're getting, let's say, with this design that specifically focuses on sequence alignment compared to, let's say, accelerating any, let's say, DP computations in general. And I guess that's probably, and also that's, again, like one type of result that I would like to see in this paper. But the second, I guess, I'm not sure if there are papers actually discussing this, but the other thing is, like, how much of the area and the power that we end up, let's say, utilizing compared to the all types of computations that you're using, right? You're doing when using that part of the hardware. So think about the entire lifetime of the hardware that you're using, and given like all the instructions that this architecture or hardware executes, what is the ratio of the instructions that essentially you're using for that particular application over all the instructions? And I guess this sort of gives maybe a clue also about like how much of the power that you're wasting, let's say, or utilizing that, I would say. And I guess like if you had supported it, basically, if you of course like support DP operations in general compared to supporting sequence alignment, then your utilization is definitely better. So then the question is like, if you have this hardware and then support this type of operations in for cloud computing, let's say in servers and so on, right? like what is the waste of power of this approach compared to, like, again, accelerating any BP operation? And is it worth basically the acceleration benefit that you get with this approach compared to, again, like whatever the abstraction level that you get? So maybe this is not, again, like very scientific, like if you really want to think about all, like if you want to listen to our servers and so on, and what will be total waste or something, but I think that's maybe like the one also direction that's good to look at that. But again, I guess this paper provides nice ideas and probably a good direction to go. I hope that's all. Thanks again for the representation.
So before we call the day, please check that we have after session quizzes. It's going to be open until like tomorrow this time, so you have like 24 hours to answer questions. And we have some evaluation forms as well. So one of them is going to be used by the presenter to share the thoughts about the menus. So basically, Victor, for example, he can share his thoughts about John and Nicholas. And the other form can be used for other students to share their feedback to the person. So yeah, you will see all this information. Just make sure to check that. And thanks a lot. I think we had two exciting presentations, excellent talks, and hope to see you all next week. Thank you.
Sorry?
For providing the laptop and the setup.
Sure. Yeah.